idea to bring a computer next time. And then you can go over, with very specific instructions to get the Python on the computer. One of the good thing about Python is, it's like a notebook that you can have the code kind of run, and then it will show up on the same screen. You don't have to switch back and forth. There's a problem with a lot of those other computation softwares. So, but we can go 2 lectures or 3 lectures depending on how fast we can go. But I think the goal is to really go take it slow, but kind of explain in great detail what each of those means, and then you can some of the code that may be useful for your project, and maybe not. So we don't know. Okay, so all right. I have been forgetting about Jared online. Jared, you hear what I'm saying?
Oh, it's on there. Yes.
Jared. Do you all hear me? I have been speaking. It's
Really weird. What did you say?
Okay, there's something coming. Can you hear me, guys?
Like, we can hear you, North Platte.
You say you can't?
We can.
Okay, great. So you know what's the charge for today, is it right?
What's that? Sorry, once again?
You know what we are going to do today, is it right?
Sure.
Okay, so I will go over then. We have 3 groups for this class. So what I'm going to do is I will ask a biomedical engineer group first to talk about their project, and then I will switch to North Platte. And then we'll have the agricultural group to talk about their simulation study. Does that sound like a good plan? Okay, all right. So, I don't know what's the best form, and I can do this. I can kind of point to the computer to them. You made a PowerPoint, or that's even better. So, yeah, no, even one slide is fine. So, who wants to come up, or all of 3 come up, and then. So, is there any way to open it up on my computer? Or you have so that's great. So
We were actually meeting the other day, we sent an email, so.
we are organized.
Yeah.
And motivated.
Well, I think we're
Not
just.
so much about that one.
I think we're just better at pretending. Okay, now Jake, I can turn on the projector. I feel like it's on Zoom.
Yeah, the projector's on. I hit. Yeah, something's off.
Interesting.
Because the bulb was on, but nothing was projecting.
Yeah.
We'll just try toggling. Turn it off, turn it on.
How do we get this on Zoom? Is it on Zoom already?
Now it's refusing to turn on.
Oh, you mean screen share?
Yeah, I don't know how to screen share.
Here.
here. Maybe. Yeah.
It's not responding anymore.
Not responding.
Okay.
No. Okay. So that's okay. So now that people folks can see it, right, through this meeting. So maybe just turn around it.
Yeah,
Okay.
you guys.
We'll see it.
Do you do anything other than hit the on button?
I didn't do any particular thing today. And there used to be a remote here. Is it the app song?
Sometimes after you turn it off, it requires a little while.
A little while to respond. Yes.
Yeah.
Right. Yeah. So give it some time.
Yeah.
It's telling me what to do here, but somebody ripped off half of it, so I don't know what buttons to push. It says press something and off buttons simultaneously. So.
Oh, it's stop thinking. So try hitting on now.
Yeah.
Mm.
All right. Maybe turn around. Yeah, we can.
Okay.
Small things.
It was.
Yeah, I do
So,
think
maybe
it
it
needs
says
some time.
something
Once you turn on, turn it off, and then pass some seconds for it to respond.
Yeah, I guess we can just
Yeah.
talk and
Yeah.
we have some pictures, but maybe you guys will have to come and look at them if you really want
Yeah.
to see them. Okay. Okay, so I'm Benton. This is Jake and Eric, and yeah, can you hear me, Jared? Oh, you're muted, so I'm just gonna assume you can hear me.
We can hear you.
Oh, good. Good. Thank you. Yeah, so our final project is about some data that we got from another professor in our department, Dr. Forrest Kiewit. He does research on traumatic brain injury, and he is trying to develop nanoparticles which he can deliver into the blood, and they'll go into the brain and kind of selectively go to the site of the injury, and maybe he can attach some drugs to those particles, and so it'll be kind of like targeted delivery of drugs to where the injury occurs. Okay, something's happening. Yeah, good. Thanks, Josh. Okay, our projector's turning on, so that's good. Okay, so yeah, so they do MRI images of these mice after they give them very controlled knocks on the head, basically, to study how the nanoparticles are reaching the site of injury. So what we want to do is we want to identify in these images which part represents injured brain tissue and which part represents healthy brain tissue. So it's a segmentation problem. I'm just gonna go to the slideshow here. Okay, a previous student did some work already. He used a unit, and one of the problems that we were facing was we only had about 204 images that had brain injury on them. So he augmented it using flipping and rotations. Then he saved 68 images for validation, and he got a decent Dice coefficient for his segmentation. Was that for segmentation? I'm actually not sure.
Yep.
Okay. I'm not sure how you calculate Dice coefficient for something that's not
If you guys
binary.
remember all the way back to the first presentation here, Jake actually talked about it.
Okay.
Do you remember any of the specifics?
I believe it's a ratio of false positive and false negative, but it's essentially just how far off you are. So basically,
So maybe it's helpful to specify what's the range and what is considered to be a good classification result.
Okay. Oh, we'll continue then.
Yeah.
Okay. Someone else want to talk about the next slide?
Well-
Oh, well,
I can't explain it. So 0 to 1 is the range for high scores.
Okay.
And then for the human brain imaging, they were finding 42%, I think is what I presented on. And then they had some segmenting at or 0.52 is what some of the good algorithms were, and they think that the iterator performance was somewhere around like 0.54. So if this was the same as human brain imaging, it would actually be better than iterator accuracy, which is pretty good.
Alex did have some concerns about overfitting now.
We'll get to that in a little bit. Okay, so our goal, like we said, was we just want to design a neural net to segment the injured tissue from the healthy tissue. Okay, so our data, like Jake was talking about, we've got images with brain injury. There's 272 images, but they're really duplicates taken at different MRI settings. So there's 136 total images with 136 masks that have already been made for us. I don't know, if you look very carefully, you can kind of see this kind of grayish shape here. That's the mask showing where the injury is. It's overlaid on the image of the mouse brain. And these are just the two duplicates.
That's where the injury is.
Yeah, that's where the injury appears.
It's some sort of pin thing hit on the top of the head, so it's fairly controlled. It should be appearing in basically the same spot every time.
Okay, and then these are mouse brain images without injury, and it's not that easy to tell by eye. Yeah, that's what the data looks like. And there's a lot more non-injured scan slices than there are injured images. Okay.
So one of the things we were kind of thinking of is how do we expand upon what Alex has done so far. He's kind of done the standard approach using a UNet and doing some augmentation, and so we were trying to figure out how we can do something better. And one of the things we came up with is trying to take the non-injured data, so the non-injured slices, actually creating fake injuries, so simulated injuries. So we'll create kind of a shadow on the MRI that should look like an injury, an actual injury. And then we'll train on this extremely large set, because I think we have something, what was it, 1172 or something. So if we have like 10 different injuries, fake injuries that we can overlay and rotate and stuff like that, we might be able to get, like 11,000 images, and then we can augment those, and we can get a huge data set to get this model trained on. So we'll train it essentially on a simulated data set, and then we'll train it, we'll kind of do some transfer learning and train it on the actual data and see how that performs in the end. And we're hoping that it gets it closer. And I think we're gonna also look at if something like random pixel brightening might help, because if you brighten a pixel, that shouldn't be picked up as damage. So just kind of throwing some random things at the neural net might help it to reduce overfitting. We'll also try things like rotating mirroring and adjusting brightness and contrast. And then of course, we'll try tuning some hyperparameters, like the amount of dropout and stuff like that, to control overfitting, because we think that's a major issue. And then we plan to use Python and a UNet architecture. Who wants to take it?
All right, so this is ideally what we come out to have. We want to be able to select out the area that has an injury, and then we'll compare it to the ground truth and get our results that way and decide where we need to go from there. Obviously, we want that to be as close as possible without just completely overfitting our data. That's kind of an example of what we want the outcome to be.
One question is, how would you, this is a good example. You got a ground truth mask, which seems to be smaller than your predicted mask, right? And I assume that, you want those, the shape of predictable ground truth as close as possible. And you may, how you evaluate this, because this isn't gonna be, like a 1 or 0 type of classification. This is more. So do you have, I guess if, you have a good prediction, then you're not only being able to tell if there's injury or not, but also have the pixel size and area identified pretty much overlay to your ground truth.
The dice score takes into consideration.
Yeah.
Because it's the dice with the,
Yeah, a lot of people sometimes they'll look at the false positive and the false negative rate, but a lot of times they use the dice score and then I think Hausdorff distance, which the dice score is kind of like generally the errors, but it's less sensitive to outliers. But then the Hausdorff distance looks at the worst outlier. So those two kind of give a good indication of how it's fitting.
but yeah, I just want to make sure those being captured by validation.
Yeah.
Definitely dice score, at least.
Cool.
Is
Okay,
that-
so
Yeah, that's it.
are there any other questions from you guys? No? Okay, so any questions from those flat folks? If you have any questions, you can type it in our conversation box, or you can, just speak up.
No questions.
Okay.
Go ahead.
Oh, she said, I think she said no
There's
question.
no question. Okay.
Okay.
All right, well,
Okay, thanks
thank
guys.
you. That's nice. I look forward to it. And so, Hope, Jared, and Abia, right?
When will we be presenting this?
That's a good question. So the question is when we are going to be presenting this. So, given this is a graduate level course, it is, I have, when I teach graduate students, this kind of a class and recognizing this is new and, maybe there's a lack of, expertise just overall, right, as a whole, that, we don't do this kind of stuff yet on a regular basis. So I am, try your best to be able to complete the project. And we can certainly set up a time, like, right before the data week, and then we can, kind of have a presentation and then, and go over this whole thing more comprehensively and holistically, and look at the results and the future work suggestions. But don't be pressured by that. Okay, so I'm perfectly fine that if you come to me saying we are still working on that, but we're not quite to get to where we want to be yet. I really I think this is it is more important for me that you have a good product rather than you are trying to kind of compete with the time, like trying to finish everything in a hurry. So does that make sense? So if all of you can complete the project by the end of this month, I guess that's when is the data week? When is the week that everybody is gonna prepare for the final? Last week. Yeah, I thought that. I can look up the calendar. So and let's shoot for that for a presentation of all 3 projects. But again, make sure that you do good work rather than trying to wrap up everything in a hurry. Okay, and you present what you have, and it's between you and me, for kind of assign a grade, right? And I specify that at the very beginning that this is a graduate level course. If you show that you are participating and you are actually kind of participating in the discussion in the project, you're not going to get get something below A. Okay, so that's my kind of position here. Okay, but yeah. Does it make sense?
Yep.
Okay, so does that make sense to you, North Platte?
Yes.
Okay, all right. So now you guys are up next. I don't know if if you have a slides, great. You can show it now. If you don't, maybe you can just talk through what's your project objective. What you have up to this point, or where this is going.
So we have slides and would like to share them.
Great. Yes. And we now have the project working. So please, let me see. Maybe I'm not doing the right thing. Group chat. Oh. How do you maximize this thing?
I think you're sharing one of your slides, so we cannot be able to share.
Oh yeah, okay, maybe because I'm still sharing here. Stop share. Okay, yeah. All right, so I think you can share now. You should be. Okay, all right, cool. So we can see it, perfect. Is someone talking, or there's nothing coming out of the microphone here?
Okay, sorry, we'll start again here.
Okay.
So our project is about detecting nitrogen stress in corn using machine learning. My name is Jared Bailey. I've been asked to speak for the group for the most part. Hope and Navia are also here with me. And our project is based on a project that I've been working on for the past year, and Navia and Hope have started working on recently, also called the TAPS project. So in the TAPS program, this program was developed to use producers, actual farmers in Nebraska and Kansas, to test new types of management practices on simulated farms. Over the past 2 years, we've had actually 32 simulated farms where each farm is replicated 3 times over approximately an acre. And we do all of the management, but the producers make all of the decisions concerning irrigation, fertigation, hybrid selection, marketing, these kinds of things. And they're actually competing for the best yield, efficiency, and profitability of their simulated farm. And included in these farms, we have control farms that are not managed at all. They're just there with the corn on them growing without irrigation or nitrogen or anything else. And the types of nitrogen management that the farmers can make decisions on include pre-plant application, side dress application after emergence, and then 4 different fertigation applications during the growth period of the corn, that V9, V12, R1, and R2. And of course, the importance of nitrogen, there's it aids in all kinds of things in the plant, including the photosynthesis, how efficient that process works, the growth, the vigor of the plants. Lots of things concerning the health of the plant are tied to nitrogen just because it's organic. So, so how do we measure the nitrogen in the plants? We do measure the nitrogen in this study using leaf tissue sampling, which is a pretty common way of measuring nitrogen in the plants. The problems with it is that you are actually going to damage the leaf. It can be time consuming if you have to send it off to a lab to have done. Of course, you have to pay for that. And due to these things, it's just not very conducive for real-time management of the plants. I don't think any of our participants in the TAPS program actually used the tissue sampling results for their decisions very much, because it was just kind of too late by that point to use them. So we'd like to see something that's a little more real time that can be done quicker. And that, of course, would be one of the reasons we want to use machine learning. Non-destructive, of course, inexpensive once you've developed the routine, and then can be done rather quickly compared to sending it off to a lab. So our objective is to use this existing TAPS imagery that we have from the project, and we took pictures. We took quite a few pictures, but we'll see some more information about that in a minute. And we want to use this machine learning or neural network, whatever, to try to detect this nitrogen stress. And of course, we're going to have to identify the imagery to be used. We're going to have to sort it in some way through the testing that we already did with the nitrogen, with the leaf testing, and then develop a network. And we're going to use MATLAB for that. And then, of course, to analyze this for subsequent studies. So the imagery that we actually collected during this project was in 2017 we had 12 farms, 1 control, 11 competitors, and we took imagery about every 2 weeks from emergence to harvest. It was a little bit longer than that sometimes, because we tended not to take pictures when it rained, just because the fields are so muddy. And then in 2018, we had about 20 farms, 1 control, and 19 competitors. And we took in images a little bit more often from emergence to harvest. And we're actually doing this next year also. So far, I think we have some 28 farms maybe, or something like this. I can't remember exactly. So it's increasing each year. And so if we continue with this, which I think we probably will, we will have more data each year. We've identified 62 favorable images from the combined years, and 12 from farms that definitely had no nitrogen application or very little, and then 50 with more nitrogen than the average. So as we went through the images, we tried to decide which ones would help us in this project the most. And things that we found favorable were consistent lighting, open leaves that are very well defined, where we can see what's going on the leaf, because that living part of the tissue is going to be where we're going to see the signs of this nitrogen stress. And then consistent coloring was quite important. And you can see that on the left picture, a nice image showing that. And then on the right, we have another image that has very high contrast. You can see some hail damage in there and inconsistent coloring. Probably not the best image to use. So we threw out a lot of images, and we ended up with only the 62 images. We think that we can probably expand that imagery doing similar processes that have been discussed, like rotating and things like that. And so we haven't got to that point yet. But at the moment, we've been resizing our imagery for use in the neural network, and we're trying to figure out the categorical array building for classifying our images. That's kind of where we're at the moment. Eventually, we would like to use MATLAB and the toolboxes to train and test a convolution neural network with our images. And of course, our expectation is to be able to train this well enough to distinguish the stressed corn imagery, so we can use it to aid in nitrogen management. It's our understanding that it's my understanding from talking to the people who know more about the biological side, as I'm learning this, that this mostly happens at the bottom of the plant. The nitrogen stress is first recognized towards the bottom of the plants, and our imagery is actually towards the middle of the plant. So we expect a little bit of challenge there maybe to have the imagery that we need for this, but we'll see if we can identify that and make it work. And I've already mentioned a couple of our challenges, but we have very few images taken considering the size of the study, and each farm was replicated 3 times for the scientific rigor, but we didn't take images of those replications because our images were not taken with science in mind. They were just taken to inform the competitors or to give the competitors view of what their farm was looking like. So definitely we would want to take more images and get those 3 replicate plots imaged better, and maybe a little more scientific method involved with our imagery. But that's, trying to find that differentiation between stressed and non-stressed is going to have to be very much a part of our process going forward if we push this project forward, so that we can take pictures that are more suited to actually seeing this stress in the leaves and the plants. So what do we expect to maybe do with this in the future? We actually think that this could be quite useful. We've been struggling to pull real good science out of this project. We can see that it's a great project from the point of view of an extension to give these farmers the opportunity to try new techniques and new technologies in their fields. But we had a hard time really deciding, can we turn this into some kind of new understanding of things scientifically, to write some papers, to do some presentations, and to kind of push the science forward. But with this, with the idea of using the neural network to track nitrogen stress or water stress or something else in this, that opens up some great doors for this project, we think. So if we can take more imagery, maybe even integrate an imaging system into our irrigation system, so that every time it's irrigating, it's taking imagery or something like this. We could also standardize our image method, our image collection protocols, so that we're getting very consistent images, maybe on the same plants, same time of day, same, all these things that are going to give us better images to choose from. But in the end, really, we're hoping that this can give us time for, that can give us data in time to make the nitrogen management decisions, and maybe even give us the opportunity to target different parts of a field for targeted nitrogen management. A variable rate fertigation system can certainly deliver nitrogen to different parts of the field and not deliver nitrogen to the parts that don't need it. So this could be a very good thing for the economics and the growth profile of the fields and the plants. So it's very promising, I think, from our point of view as the project goes forward in TAPS. But we're just kind of sifting through the imagery at this point, and that's where we're at.
Yes.
Okay, thank you. So, I think that's a great presentation, and this is a wonderful project. One of the potential problems that I see here is you only got 62 images, right? With
Yeah.
With 50 negative and 12 positive. If positive is to identify the stress.
Yep.
Yeah, so it entails us to be able to collect more images from field, and there's a lot discussed, like some of that you already mentioned, how to standardize imaging protocol, and all those factors potentially affect your image quality, all those things, right?
We actually have another study in another location that is not related to the TAP study that we can pull some imagery from, and that's been iteration, especially as we're just trying this out. So
Yeah.
that may be a real solution for us to just try to get this started. to kind of steal some images from some other cornfields. And so we do have that resource available to us if needed, which is, it's likely that we're gonna need it.
Yes.
Yeah, so this is something that I, kind of ties back to what I'm mentioning earlier about, to fulfill the class, the project itself. I don't really see that, you do a project for the class and then it ended. And, I think it would, as a student, you would be more better, if you keep this on the back, on the back of your mind and trying to, do, I don't know, maybe you can, keep this project going, even knowing that, there won't be a class anymore, like, this semester, the next semester or next season, but you can continue to collect some more images and make it a bigger database, and then coming back to test your algorithm.
Yeah, well, like we said, we were trying to figure out a way to make good use of the TAPS program scientifically, and this gives us that opportunity. And it's very likely going to turn into my PhD project for the next 7 years, since I'm going to be on the slow track because I can only take a couple of classes a year. Yeah. But this will very likely be my PhD project, using the neural networks to evaluate different things in the TAPS fields. So I think it's a very good thing to take this class for us.
Yes.
Mm-hmm. I'm glad to hear. I certainly think this got a scientific basis. I think if you look at the way that we perceive our world, vision is probably handles more than 90% of the information. And then when you see how farmers of the old generation who are trying to understand the nitrogen deficiency or the water deficiency, all those things, they are really rely on their vision, right?
Yes. Mm-hmm.
And all we do now is just to try to use the computer to replicate all those perceptions, but the system in your brain for so many years.
Yep.
Yeah. So it has certainly got a good psychological and a biological basis.
Mm-hmm.
Yes.
And maybe one of the expectations we have that at the end of this, in addition to presenting the CNN that we'll have developed, is just trying to present and maybe discuss with the class some of the ways we think we can standardize this image taking protocol. So maybe mounting some cameras on the pivot, or we've also thought of maybe trying to do destructively, maybe just literally remove the corn leaves from the plants and taking the images. So we're still trying to think about that, but then those will be some of the things that we present at the end, some of our thoughts on how we'll standardize this image taking protocol for the coming season. Yes.
Exactly. So, forced critical thinking is the thing that you all should get from the graduate training, right? But I'm gonna just kind of go out and do some random things, kind of hope that the best thing would happen. Or you have a better planning about, here are the series of choice, and I'm gonna do all these things particular way, over some other choices because of, this, right?
Yes.
Okay. All right. Well, thank you very much.
Thank you.
Thank you.
All right. So Josh and Amy, I don't know if you guys have any slides, or if don't, that's fine. You can just talk about what you have.
We don't have the slides, I guess. But...
Maybe you want to speak up so that they can hear as well. Yeah. So maybe.
So our project's kind of abstract, based on UPhone's recommendation. So we're going to be generating shapes using MATLAB. So we have basically an unlimited data set potential. So we can, the overall goal is to try to trick CNNs using optical illusion type images. So say you create a square using a bunch of circles or something like that, or you create maybe the outline of a square using triangles. That's just two examples. So our initial goal, I guess right now, is we're going to do square versus non-square detection. And we're going to train the network using, this all sounds very basic, what you guys presented, but we're going to be using squares, circles, and triangles. and then we can generate. So we have a square generator MATLAB code now, a circle generator MATLAB code. I guess I should mention our team. So it's me, Amy, the other Eric, and Jez Raymond. So we're all working on this. So we're trying to find and conquer, I guess. So we have a MATLAB script that can generate squares randomly placed throughout a 256 by 256 image. It's just a binary image. And then Eric sent me a circle generator, which does the same thing. And then I'm also working on a triangle generator. Amy set up the basic outline of a MATLAB CNN. So we'll be testing that and seeing what performs best. And then our goal is to import different optical illusion images, probably just hand generated, image process them into MATLAB as a 256 square image, and then test the neural network with that and see if it, our human brain would probably say, hey, that looks like a square, but it's made up of circles. But we want to know what does the CNN do? Is it act similar to a human brain would, or is it say that's a bunch of circles? That's not a square. So that's kind of the general outline. Pretty basic overview, I guess.
Well, just a quick comment. It's yes, probably sounds like a basic, but it's got a very profound, practical implication. That's for cybersecurity. So, somebody later on, this is probably not a problem yet. Nowadays, when it gets to, if the neural network really gets to every walks of our life, then, the ability to be able to defend the attacks, advisory attacks is going to be quite substantial. It can become very active. It is an active research area already, but it's probably going to become an even bigger role. Somebody somewhere there in some corner of the world is going to try to develop something to trick the neural network, basically, right?
So is the goal to make the neural network more robust than? Or great?
Both, just to see what happens, I guess, first, because we're not really sure yet.
Well, then you talked earlier about the self-driving cars and like changing some pixels on a stop sign turns into 55 miles an hour.
Yes.
So obviously they're trying to figure out what's happening there so they can fix that.
Yes.
So is that kind of the way that you were planning on going with this?
Yeah, it's kind of similar theory, I guess.
Yeah, I guess so. And the other thing is really see, everybody tries to compare the neural network with human brain. Now, if optical illusion really is a physiological response of human brain, right? If neural network sees the same thing, then it means it does share some similarity with the human brain that optical illusion also have an effect on the neural network. But if it doesn't happen, then I don't know what's the implication there. But that's something probably worth more research on, right? Then it seems like to be more, So, yeah. By the way, so this year, I don't know if you all see the news. So this year's Turing Award is given by those those three authors that published the very first CNN architecture. So Yashu Bengio, Geoffrey Hinton, and then Ian LePen. So those three folks, they kind of published like 1998 or something, the very first CNN paper. They got the the award this year, all four of those 2 years. But that's encouraging. It means that in this really society sort of recognize their contribution.
Short and sweet.
Yes. Okay. Alrighty. Well, thank you very much. So as I said, kind of keep working on that, and we're trying to kind of coming back and maybe I'll look at this calendar. And there's a university rules and what you can do or what you cannot do on those weeks. I don't want to violate university rules, but we can agree on a date. And then, I think, 75 minutes would be long enough for all of you, 3 groups to present the results. And then, again, don't worry too much about, fulfillment of this class or the final grade of this class. But I would really wanted to see that, this is a continuous process. Maybe, maybe you are not there yet at the end of the semester, but, we plant a seeds, maybe half a year later or 1 year later, it really becomes an interesting project, something that we can publish or kind of continue work on that. Okay. Sounds good. Okay, great. So, North Platte, do you all have any further comments or questions about what are we gonna do with the next few weeks?
No questions. If we have any, then maybe we'll send you an email. Thank
Okay. Okay, great. Well, thank you very much. Okay, so thanks. Well, looks like everybody is on the right track. It'll be interesting to see some of the results.
some artificial intelligence.